Hello, welcome back. Welcome back to another remote class session, another new week. So far we had looked at how to balance a tree, and we looked at complicated balancing algorithms such as 2 to 3 trees and red-black trees. And I should say that these are really the advanced algorithms that we looked at on how to balance a tree structure. Starting today, we will shift our focus to graph based algorithms. In this session, we will discuss what is a graph and some basic terminology in a graph, and then later we will also see how to represent a graph. So let's get started. A graph is simply another data structure. We had earlier seen data structures such as arrays. We also looked at linked list. Then we looked at trees. So we looked at arrays when we did sorting. And then linked list and trees, we looked at that when we implemented the binary search trees. So now we will get into the topic of graph. A graph is simply a set of vertices and a set of edges, which connects all the pair of nodes, right? So it connects a pair of nodes. More formally, we can define a graph as G is equal to V comma E, where capital V is the list of vertices and capital E is the list of edges. Or we can call that as a set of edges and set of vertices as well. So some application of graph or maps, like map of cities in Google Maps or any other map based engine. And electrical circuits, for example, Facebook friend list. So if you would have noted that Facebook would recommend friends, they basically do that using a graph data structure. Each person is a node in the graph, and then you could simply draw the connection of that person as a graph like this, for example. And the same thing with Amazon product data and genetic data, human genes. Each node is a genetic information, right? So there are several applications of a graph, and this is why a graph is an important concept to understand in computer science. So we will spend some time in this session to look at different types of graphs and basic terminologies of graphs as well. So with that, we will ask a question here. How is a graph different from a tree? We looked at a tree earlier, but then a tree is simply a specialized case of a graph. A tree is also a graph, in other words, right? But then a tree is a graph with no circuits or what we call as a self loop, right? So whenever you have a tree, you don't have this. You don't have a self loop. And you don't have, if you have a tree, you don't have this, you see. So this is called a circuit or a cycle. So you don't have a cycle there. When you talk about a tree, you don't have a self loop either, right? So that's two important things that separates a tree from a graph. Whereas a graph is simply, it consists of vertices and edges and a set representing the relationship between the vertices and edges. And then you can also see that there is only one path between any two vertices in a tree. If you consider a tree, if I consider this node and this node, there's only one path in a tree. Whereas in a graph, there could be multiple paths. So let's connect this guy and this guy. So now watch. Now you have a path right here. I'm talking about this path. Or you can go using this path right here, which is this path, right? So there are two paths which makes it a graph. It's no longer a tree, right? So every time you have any number of paths between any two vertices, then clearly then that becomes a graph. A graph can contain a loop, by the way. A graph can contain a loop, whereas a tree is simply a minimally connected graph without any loop. So we will look at minimally connected graph in a minute, but in general, we can say a tree is simply a graph that has no loops and no circuits. And a tree should also be connected. As you can see here, all the nodes are connected in this tree, but there's no loop. I mean to say self loop, and there's no circuit. Whereas in a graph, clearly there is a circuit right here, which is simply a cycle, right? So you can see all these nodes are connected, and thereby it's a graph. It's no longer a tree, right? And then the second example of a graph is as well right here. So anytime you have a connected graph with a cycle, then clearly it's no longer a tree, right? So you can see that this guy is a graph and it's not a tree. So some types of graphs here for us to look at. We have a directed graph where there is an edge between two nodes, and the edge decides where is the source and where is the destination. So oftentimes 1 here is the source and 2 is the destination. And then an undirected graph has no real arrows, right? So 1 is connected to 2, 2 is connected to 1. Whereas in a directed graph, 1 was connected to 2, but 2 was not connected to 1. That's the difference between directed and undirected. A weighted graph simply has a weight for the edge. Each edge has a weight. And when we talk about later on, when we talk about minimum spanning trees, we will discuss an algorithm which will make use of this weight here. But for now, let's understand that there is a notion of weighted graph in a directed graph here. And as well as in an undirected graph, there's a weight for each edge. And there is a notion of connected and disconnected graph. A connected graph simply consists of a path between every two vertices. So you look at this graph right here on the left side. For example, if I would pick 2 and 1, or 2 and 4, let's say, there's a path between those two vertices. And if I pick 6, then there is a path right here. And there's also a path from 2 to 3 to 3 to 6. Whereas a disconnected graph, clearly you can see that this particular section is disconnected from this section right here, right? So there's no connection between 2 and 3, and thereby it's a disconnected graph. A strongly connected graph will make sure that every two vertices are reachable from each other. So if I want to connect A to B, there's a arrow that connects A to B. And B to A, there is also a connection right here. You see? There's also a connection right here. And the same thing is applicable for all the nodes. All the nodes will be connected from each other. A weakly connected, if you take this, let's say if I just get rid of this here, if I take this graph and I remove all the edges, right? So let's say in this particular graph right here, we take all the arrows, convert that into an undirected graph. If you make that conversion and if you find that the graph is connected, then it's called weakly connected graph, right? So you take the original directed graph and make it undirected, and then you check if it is connected or not. If it is connected, undirected graph, then simply it's called a weakly connected graph. So let's look at some basic terminology. We talked about source and destination earlier. A directed edge is said to be outgoing on its source vertex. So for example, edge AB, A here is the source, or the source, and then the outgoing edge is defined on the source. And then a directed edge is incoming on its destination vertex. So B now has an incoming edge, and A has an outgoing edge. So there's something called a degree here of a vertex, which is simply the total number of edges connected to that vertex. So there's in degree and out degree. You can see that in degree is the total number of incoming edges. Out degree is the total number of outgoing edges. So if I simply pick B, B has one incoming edge. So clearly you can see that the in degree of B is 1, and B has 2 outgoing edges. So you can see out degree is 2 right here. And the total degree is simply the sum of in degree and out degree of that particular vertex. So a degree of a vertex is very popular. It tells if a node is popular. For example, let's say that in the Facebook friend list, if you have a person, Mark, who has his friends like this, if there is like so many outgoing edges for Mark, so then clearly Mark has many friends, right? If you assume that there's a guy Bob, and then Bob is connected in this fashion, all incoming edges to Bob, so then you can say that Bob is being connected by many people, right? And this is an outgoing edge for this matter. So clearly you can see that the notion of in degree and out degree is very important in the term of a graph to decide how popular a particular node is. So we will quickly look at one property of a graph here. A graph, if we assume that a graph G has V vertices and E edges, then usually the number of edges is less than V square. V is the number of vertices. If E is closer to V log V, then we call that graph as a dense graph, which is also too strongly connected and is in a complete form. So we will pick one example. Let's say that you have a graph like this. You have the connection right here. So you can see clearly that this graph has a connection between all the nodes, right? So thereby there are 6 edges here, as you can see. So you can assume that this particular node is connected here to 3, and then this guy is connected 1, 2, 3, 1, 2, 3, so on and so forth. All the nodes are connected, right? So this is why you have 6 edges right here, and then you have 4 vertices. So in this case, you can clearly do the multiplication yourself, which is going to be 4 times log 4, which will be 4 times 2 log 2, and thereby you have 8, right? So if the number of edges is closer to 8, then it's called a dense graph. If it is lesser, then it's simply called a sparse graph, right? So sparse graph, for example, would be something like this, where there is a minimal connection, right? So you can call this as a sparse graph. Whereas if you have a connection like what we've seen right here, then it will be more a dense graph. We will get to that point in a little bit, but for now, let's understand the difference between a dense graph and a sparse graph. So in other words, a dense graph would be a graph that has many edges, many edges. And a sparse graph would be having lesser number of edges. So how do we represent a graph in our program? Let's say a Java program or a Python program and so on and so forth. There are popular two ways to represent. One is the adjacency matrix and the other one is the adjacency list. Usually you use an adjacency matrix on a dense graph and then adjacency list on a sparse graph where the number of edges is lesser compared to the one in a dense graph. We'll look at an adjacency matrix first. So an adjacency matrix would be a two-dimensional array. Let's call that a 2D array. And then you have 0 and 1. If if there is a vertex I and j that are adjacent to each other and they are connected by an edge, then you simply make that element as 1, 0 otherwise. Right? So if A is connected to A, then you make it 1. If A is connected to B, then you make it 1. For example, right here you can see B is not connected to C, so you make it 0. So on and so forth. An adjacency list on the other sense, has list of an array of vertices 1, 2, 3, and each item in that array is connected to a linked list. And this linked list would simply show all the connections. So what we mean here is the list item I contains vertex j if there exists an edge I comma j in graph G. If that exists, then you would simply going to create that item. So here 1 is connected to A. This is node 1 which was connected to A, and node 1 was also connected to B, and node 2 was connected to C, so on and so forth. So the space complexity, let's go back for the adjacency matrix. A space complexity is order of V square, where V is the number of vertices. Clearly you can see that if you have a 5 vertices in a graph, then it will be a 5 by 5 matrix. If you have 25 vertices, then it will be 25 by 25 array. So clearly it's going to be V square, right? So the order of V square is the space complexity, which is how much space it would roughly take. Whereas an adjacency list in the other sense would be, firstly, we need V space to store an array of V items, and then each item may hold up to 2E edges. Why do we say that? If we go back and draw one graph here, simply, let's say we have this graph. So you can clearly see for each of them, each vertex, I should say a pair of vertex, there's an edge, and this edge will be counted twice in a undirected graph, right? So why? Because 1 is connected to 2, and 2, I should say 1 is connected to 2, 2 is connected to 1. So it counts 2 times. Each edge counts 2 times, and then thereby you would say that the space complexity is order of V plus 2E, where E is the number of edges. Okay. So clearly we need a space complexity of total of V vertices, capital V plus 2E, because each of them, each edge would be counted twice in an undirected graph. So we'll look at some examples to further claim the understanding of this graph representation. So if we take this graph right here, so you can see that there is no self loop. If there is no self loop, you can clearly go and say that the diagonal element in that array or in that matrix would be 0, which means 5 is not connected to 5, 4 is not connected to 4, so on and so forth. If at all, if you have a self loop, as we will see in our practice problem, then you would want to make sure that this guy 3 3 is not 0, it's 1, right? So which means 3 is connected to 3, but in this case it's not, so I'm going to remove that and then make it 0 as it was originally. And then if you take an undirected graph, here you can see why it was order of v plus 2e. Clearly, for each edge between those pair of vertices 1 and 2, you can see that we had counted it once, and then 2 was connected to 1 again, right? And here, if you make this as an adjacency list, then it would be order of v plus 2e, but here it's a matrix, so it would be order of v squared, right? The adjacency matrix. Example 2 is where we will show the directed graph and then the adjacency list. First thing first is we need to have an array right here with all the vertices. If there are v vertices, then you would have v number of elements in that array. So here there are 5 vertices, so you would have 5 elements. And then 1 is connected to 2, 1 is connected to 4. So you can see 1 is connected to 2, 2 is connected to 4, 4 would be connected to null because it's a linked list, right? It's a singly linked list. So 2 is connected to 3, again you can see that, and then for 4 you can see it's connected to 2 and 5 and null, so on and so forth. So if you take up the undirected version of it, here you can see clearly that each edge is counted twice. So 1, 2, 3, 4, 5, 6, you would have 12 items in your linked list. So 2, 5, 7, 10, 12, right? So clearly it's order of v plus 2e in terms of space complexity, because this is order of v anyway, and then this guy, the linked list, would be order of 2e, right? So there's a tryout problems here for today. I'd like you to try out this graph given here. Come up with the in degree and out degree for all the vertices. So there are vertices starting from A all the way to J. So you may want to measure the in degree and out degree for all these vertices. Please do your posting in the general channel. You can write up in your notes and then take a picture of that and then post it there. Tryout 2 would be given this matrix, and you would see that there is some self loop in this matrix, right? So please make sure that you include the programmatic representation using adjacency matrix and adjacency list for this given graph, and post it in your in our general channel as well to get the class participation points for today. So the next step for us would be to look at traversal algorithms. We will look at BFS and DFS this week. And then next week, we will look at shortest path algorithm like Dijkstra's algorithm. And then we will also look at some minimum spanning trees, trims and Kruskal's next week as well. And all this discussion is going to be primarily based on our textbook, Sedgwick 4.1, 4.2. Please take a minute to do those reading assignments as and when it's required. And don't hesitate to ask any questions. So today is the first day for us to get started on this topic. But we are going to go more advanced in the next subsequent lecture. and we will cover a lot of graph-based algorithms in the upcoming classes. But please feel free to reach out to me if you have any questions related to this discussion. You can reach me through Slack, email, or even during the office hours as well. Okay, with that, I'm going to end this session here. And again, thank you for watching this video.